All right, let's dive into something that sounds, well, kind of crazy. What if I told you that you could solve some of the hardest problems out there just by using randomness? It feels like it shouldn't work, but it absolutely does. So let's see how. Seriously, think about this for a second. How on earth can throwing darts completely at random help you figure out pi? It sounds a little nuts, right? But this one simple idea gets you to the very core of what the Monte Carlo method is all about, finding stunningly accurate answers inside of pure, unadulterated chaos. So here's how we're going to break this down. First, we'll get our heads around this whole idea of using randomness to solve stuff. Then we'll put a formal name to it, the Monte Carlo method. After that, we'll open up a toolbox we need to generate the right kind of random numbers. We'll even see how to master the legendary bell curve. And finally, we'll wrap it all up by looking at why any of this actually matters in the real world.
Okay, so, sometimes a problem is just a monster. The math is a nightmare, there are a billion moving parts, and trying to calculate a perfect direct answer is pretty much impossible. When you hit a wall like that, you need a new game plan. You need to stop looking for a perfect answer and start playing the odds.
And here's the beautiful, simple idea at the heart of it all. Instead of doing one gigantic, impossible calculation, we're just going to run a ton of tiny, random experiments. Think about those darts again. If you throw a few, it's just a mess. But if you throw thousands and thousands of them, a pattern starts to emerge. The ratio of darts inside a circle versus inside the square around it starts to tell you something. A lot of something, actually. The more you throw, the closer you get to the real answer. It's about finding the hidden signal inside the noise.
Now, this whole clever trick of using randomness isn't just some party trick. Oh no, it has a proper name, inspired by, you guessed it, the world-famous casino in Monte Carlo. So let's get formal and see what the official definition looks like.
So there it is, the Monte Carlo method. It's a fancy way of saying we're going to use a huge pile of random numbers that follow a specific pattern, that's the distribution part, to nail down a single concrete value, a value that isn't random at all, like the true area of a weird shape, or say, the probable future value of a stock. And you don't have to take my word for it. This is where it all comes from. These are the actual handwritten notes that this whole explainer is based on. You can see it right there. The definition we just saw, it's pulled straight from this page, a statistical sampling technique used to evaluate a non-random quantity. This is the real deal. Okay, this is absolutely crucial. We don't just need random numbers. We need random numbers that follow a very specific recipe, a particular shape or pattern. The problem is computers are, well, they're kind of basic. They're great at generating simple, boring randomness where every number is equally likely. But how do you turn that into the complex, beautiful patterns we see in the real world? Well, you need a toolbox. Let's open up that toolbox. The very first thing we pull out is probably the most important tool in there. It's called the inverse transform method, and it is a truly elegant piece of math that lets us twist those simple, uniform random numbers into almost any other shape we could possibly want. So how does this thing work? It's basically a three-step recipe. First, you need the formula for the pattern you're trying to create. Statisticians call it the cumulative distribution function. Next, you ask your computer for a super simple random number between 0 and 1. We'll just call it u. And for the final step, you plug that u into your formula and solve it backwards for x. And bingo! The x that pops out is a perfect, brand new random number that follows the exact pattern you were hoping for. That sounds amazing, right? But there's a catch. Of course there's a catch. What happens if that formula from step 1 is just a beast? Something so complicated that you can't actually solve it backwards. What if the algebra is literally impossible? Are we just stuck? Not a chance. This is where we reach back into our toolbox and pull out something even cooler. It's called the acceptance-rejection method, and it is an absolutely brilliant workaround for this exact problem. It lets us get the random numbers we need, even when the math gets nasty. And this picture shows you exactly how it works. It's so clever. Let's say that green curve is the complex pattern we're trying to sample from. What we do is we draw a bigger, simpler box around it and just start throwing random points everywhere inside that box. Now, here's the rule. If a point lands under our green curve, we keep it, we accept it. If it lands above the curve, we throw it away, we reject it. Do that thousands of times, and the collection of points you kept will perfectly map out the complex shape you wanted in the first place. So to put it more formally, here's the algorithm. You generate a candidate number, y, from a much easier to work with distribution. Then you generate a second random number, u, that's going to act like a coin flip to decide if you keep y. You do a quick check, a simple comparison. If it passes the test, awesome. You accept y and add it to your list. If it fails, you just toss it out and start the whole process over again. It's basically a quality control checkpoint for random numbers. All right, let's take these amazing tools and use them to tackle the undisputed king of all statistical distributions, the normal distribution. You know it as the bell curve. It's literally everywhere in nature and science, from IQ scores to stock market fluctuations, but making one from scratch is notoriously tricky. So for this job, we need a very specialized tool.
And that master tool has a fantastic name, the Box-Muller algorithm. This thing is a work of art. It's a beautiful piece of math that takes in simple randomness and spits out perfect bell curve randomness. And the crazy part? It makes two of them at the same time. The whole process is just so slick. You start with two totally independent, boring, random numbers between 0 and 1, the kind any computer can spit out all day long. You feed them into two special formulas, one with a square root and a log, the other with a sine or cosine, and what comes out the other end? Poof. Two completely independent random numbers that are perfectly, beautifully, normally distributed. It really is like mathematical magic. And here it is in action. This is the payoff, pulled right from the data in our source notes. Look at the left side, just simple, uniform numbers, things like 0.587, 0.030. You run them through that Box-Muller machine, and look what pops out on the right. Those are your classic bell curve numbers. This is what I'm talking about. It's pure statistical alchemy, turning boring random numbers into statistical gold. So we've got this amazing toolbox. We can create pretty much any flavor of randomness we could ever want. But so what? Why did we go through all that trouble? Well, because this isn't just some fun math puzzle. This is the engine that drives some of the most important technologies in the world. Seriously, this stuff is everywhere. Wall Street uses it to figure out the risk on trillions of dollars of investments. Physicists at CERN use it to simulate what happens when particles smash together. It's fundamental to training the AI models that power everything from your phone to self-driving cars. Weather forecasting, designing safer airplanes, you name it, Monte Carlo simulation is probably running under the hood somewhere. And that brings us right back to where we started. This quote, right from the top of the document we've been exploring, just nails it. All those incredible applications we just talked about, they all depend on one thing, our ability to generate the right kind of random numbers. That toolbox we just looked through, that's the key that unlocks everything else. So I think the real takeaway here is that by learning to embrace and control randomness, we've given ourselves a kind of superpower. It lets us ask what if about some of the most complex systems imaginable. Which really just leaves us with one last big question. If we can simulate almost anything, what's the next giant problem? In climate science, in medicine, anywhere, that's just waiting for us to solve it with a clever roll of the dice.